We have previously learned about the forces inside of molecules. These are covalent bonds that hold the molecule together. This is an example of what we call an intramolecular force. That's an internal force that holds the molecule together. In this video, we're going to explore intermolecular forces. And these are the forces that hold one molecule to another molecule. So these are between molecules, not within the molecule. If we think about solids, liquids, and gases and the difference between them from a particle standpoint, solids have order and structure, and the particles are close together. Liquids, the particles are fairly close together, but they don't have as much structure. They're a little bit more free-flowing, and they can move around a bit more. In gases, there is neither structure or order. The particles are far apart from each other, the density is very low, and the particles are just moving around kind of randomly. Now, in order for solids or liquids to hold together, that means there has to be some attractive force that pulls these particles to each other. How strong those forces are is going to dictate the temperatures that it's going to require to melt and boil these substances. To turn them from the solid to the liquid state, it's going to require an input of energy, and the tighter those particles are held to each other, the higher that temperature is going to be. In ionic compounds, we know what holds them together. There's these strong ionic bonds. It's the attraction of a positive for a negative. So the particles in the solid, for example, are, say, sodium ions and chlorine ions, or lithium ions and fluorine ions. They're oppositely charged. That opposite charge holds the whole structure together, and those bonds are quite strong. In metallic bonding, we have this mobile electron C. All the valence electrons are mobile, and as they move around within the lattice structure made of ion cores, in other words, the nucleus and all the non-valence electrons, the attraction of the mobile electron C for the lattice of positively charged ion cores, that's what holds it all together, and that's reasonably strong most of the time. But what holds neutral molecules and atoms together? Atoms and molecules don't have a charge, like ionic compounds, or like ion cores and mobile electron C. So what holds them together? We know it must happen because there are molecular substances that exist in the liquid and solid state. What holds them together are these intermolecular forces that we're going to examine now. Some molecules, as we have seen in earlier videos, are polar molecules. Because the bond dipoles don't cancel each other out, one side of the molecule is more negative than the other side. That's the side that has the greater electronegativity. Because one side is slightly positive and the other side is slightly negative, if there is a group of polar molecules around each other, the positives and the negatives attract each other and stick together. Here's another view of this. We see plus and minus attracted, plus and minus are attracted, minus and plus are attracted, minus and plus are attracted. Here we have plus and minus attracted to each other. So what's going on there is the attraction for opposite charge, just like in ions, occurs, but it's quite a bit weaker. These are called dipole-dipole interactions because they're interactions between dipoles. Sometimes they're called dipole-dipole attractions or dipole-dipole forces. And just to give you an idea of their strength, they're about 200 times weaker than a covalent bond and about 600 times weaker than an ionic bond. Let's say, for example, that this was hydrofluoric acid. So this would be the kind of the Lewis structure of it. The fluorine side of the molecule is going to be more electronegative than the hydrogen side, and so there's a dipole this way. And on this molecule, it's an identical molecule, the same dipole exists. So the bond that holds this hydrogen to this fluorine, that's the covalent bond. That's an intramolecular force. And the same thing here. This hydrogen is held to this fluorine by a covalent bond. Those two covalent bonds are about 200 times stronger than this intermolecular force that holds the one HF to the other HF. In the special case that you have in your molecule an OH bond, an NH bond, or an FH bond, then the dipole-dipole interactions are particularly strong. especially if there is a lone pair on a neighboring molecule. So here's an example. That water is a very classic example of something that does this type of intermolecular forces. So the oxygen end of a water molecule is more negative than the hydrogen ends because it's more electronegative than hydrogen. And then if you have, and you're going to have lone pairs here too. If you have a neighboring water molecule, its positive end, its hydrogen end, is going to be attracted to that particularly negative end of this very strong dipole. And that's going to happen, here, because there's a lone pair here, pair of lone pairs. And there's another particularly strong dipole-dipole interaction between water molecule to water molecule to water molecule. This special case of dipole-dipole interactions goes by a special name because it's extremely strong. It's called hydrogen bonding. So let's not get confused. The bond of this hydrogen atom to this oxygen and this hydrogen atom to this oxygen, those are intramolecular forces. Those are just covalent bonds. Hydrogen bonding is the between molecule interaction. That's called hydrogen bonding. And it's about 5 times stronger than a regular dipole-dipole interaction. We can see that with the contrast between water, which has hydrogen bonding because it has an OH bond in it, and H2S, which is a very similar structure, but does not do hydrogen bonding because there's no OH bond in there. H2S has a boiling point of negative 60 degrees Celsius, which means it's a gas at room temperature. Water, we actually have to heat it up in a kettle to make it boil, and that's because the hydrogen bonding is much stronger than the ordinary dipole-dipole interactions that happen in H2S. So that explains what happens between polar molecules and between polar molecules that are particularly strong because of the fact that they have an OH, an NH, or an FH bond in it. But how do things that aren't polar stick together? Because they do. Candle wax is a great example. It exists as a solid, but there are no polar bonds in the entire structure, which means that dipole-dipole interactions cannot explain that. Same thing with gasoline. Gasoline is a mixture of hydrocarbons. These are compounds that do not contain any polar bonds at all. So they're completely nonpolar, but yet it exists in a liquid state. So there must be some explanation for that. And here's what it is. As the electrons are constantly randomly moving around within their orbitals, for an instant, a dipole could be set up if the electrons happen to be on one side of the atom just randomly rather than on the other side. That's called an instantaneous dipole because it only happens for an instant. Might look something like this. In a neon atom, which is totally neutral, the electrons in the neon might find themselves just by chance on one side of the atom rather than the other. That sets up an instantaneous dipole because the electrons happen to just randomly be on this side. That side is more negative, and because they are not on that side's more positive. This creates a dipole in a neighboring atom because those electrons are now attracted to the positive side of this neon, and on the other side of that neon, the electrons in that neon are going to be repelled by those electrons, and so they're going to move away. And so that's going to create on both sides of this neon induced dipole. So induced means like forced to happen. So this instantaneous dipole induces dipoles in the neighbors, and then you have this attraction for plus to minus, and that's going to happen over here, and then that's going to cause another one over here, and then that's going to cause another one over here. So you have this chain reaction of instantaneous induced dipole pairs that hold together by their attraction. Now they're instantaneous, so they're going to dissipate very quickly, but they do attract the particles to each other for a short period of time. These attractions are called London dispersion forces, or sometimes they're called van der Waals forces. Those are named after two people who did studies in this area, or sometimes quite often, they're just called dispersion forces. They're quite weak. They're about 200 times weaker than a dipole-dipole interaction, and remember, a dipole interaction is about 200 times weaker than a covalent bond, so these are not very strong. However, there are some things that influence them to be relatively stronger or weaker. One of them is the size of the atom or the molecule. Here we have noble gases arranged in increasing size order. So helium is at the top of the column, that's the smallest one. Radon's at the bottom of the noble gas column, that's the largest one. And you can see that the boiling points go up as the size of the atom increases. The same thing is true for these halogen molecules. F2, that's the top of the halogen column. Iodine is at the bottom of the halogen column. And again, we see the boiling points get bigger as the atoms get bigger. Why is that happening? Because the larger orbitals in these bigger atoms and molecules allow the electron cloud to become more lopsided or more polarizable. Because they're bigger, if the electrons all get shifted to one side, that's a bigger difference than if they just get shifted to the side of a small atom or molecule. And that leads to larger dispersion forces. Larger dispersion forces mean it's harder to pull the atoms away from each other or the molecules away from each other, and that leads to higher boiling points. Another thing that influences this is the number of bonds that's in molecules. Here are some hydrocarbons, CH4, C2H6, C3H8. All of these are just made of nonpolar bonds. They're either carbon-carbon or carbon-hydrogen bonds, and they're all nonpolar. But as the chains get longer and longer, the boiling points increase. The reason for this is because more bonds means there's more electron pairs that can move around within those bonds, and those electron pairs can get polarized, and that gives you just more opportunities for instantaneous induced pairs to get set up between molecules, from one molecule to the next. Here's what they look like visually, just a sample from the middle and the two ends. CH4 has only 4 bonds. C3H8 has got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bonds. And if you look at the difference between the boiling points, C3H8 is much higher boiling point than CH4. If we switch to Kelvin temperatures, you can almost see a kind of a correlation here. 10 bonds in C3H8 compared with 4 bonds in CH4. If we take 10 divided by 4, we get 2.5. So that's the ratio of numbers of bonds. And if we take 231 and divide by 104, that's 2.2. So it's not exactly a linear correlation, but increasing the number of bonds almost proportionally increases the boiling point.